So we've chosen the right statistical test for our research question, and we've collected all the data. I suppose the next step is running the test.
Exactly. Now comes the part where we calculate the test statistic. With it, we can decide in two ways, either by using critical values or by using the p-value. Both lead to the same decision, whether to reject the null hypothesis or not.
Then let's dive in and start with the test statistic. I want to see how the numbers tell their story.
Now that we've chosen the right test and collected our data, the first step in the analysis is to calculate the test statistic. The test statistic is a single number we compute from our data. It tells us how far the observed results are from what we would expect if the null hypothesis were true. In other words, it measures the size of the difference between our data and the no-effect scenario. Here you see two very common distributions of test statistics. On the left, the t-distribution, and on the right, the chi-squared distribution. They both show how the test statistic behaves if the null hypothesis is true. Together with the significance level we set in step 2 before the data collection, these distributions allow us to determine the so-called critical value, which helps us make the test decision.
So, if I've got this right, the test statistic basically measures how far our data are from the no-effect scenario of the null hypothesis, right?
Exactly. Now, if the test statistic turns out very extreme, there are two possibilities. One is that with very small probability, such an extreme value could still occur even if h0 is true. The other, much more likely, is that it points towards rejecting h0.
But how do we decide what counts as extreme?
Good question. That's where the critical value steps in. Think of it as a cutoff point. If the test statistic goes beyond that point, we say, okay, this is too unlikely under the null hypothesis, time to reject h0.
And how is that critical value determined?
First, remember the significance level alpha that we set in step 2 of our testing procedure. Alpha gives us the maximum probability we are willing to accept of making a type 1 error, that is, rejecting h0 even though it is actually true. To control this risk, we define critical values. These mark the thresholds between what is plausible under h0 and what is too extreme to still believe in h0, while making sure the total probability of a type 1 error does not exceed alpha.
Could you show me how that works with a concrete example?
Since it's a two-sided test and we've set alpha to 5%, we split this probability evenly between the two tails, 2.5% on the left and 2.5% on the right. The critical values are then simply the 2.5% quantile and the 97.5% quantile of the corresponding t-distribution. These critical values mark the thresholds between what is plausible under h0 and what is too extreme to still believe in h0, while making sure the total probability of a type 1 error does not exceed alpha. Here in the graphic, you can see the different regions marked clearly. If the test statistic is very small or very large, that is smaller than the lower critical value or larger than the upper critical value, we reject h0. On the other hand, if the test statistic falls between the two critical values, we keep h0.
Okay, but that still sounds a bit complicated. You need to know the exact distribution every time and calculate the right cutoffs.
That's right in theory. But in practice, software does all of this automatically. And as you'll see, there's another approach that makes things more intuitive. Instead of comparing the test statistic to critical values, we can use the p-value method. The p-value tells us the probability of observing a test statistic as extreme as or more extreme than the one we actually observed, assuming h0 is true. It's standardized for all tests and always lies between 0 and 1, which is why it's so popular and often reported in publications.
Could you show me an example of how that works in practice?
Of course. In the graphic, the p-value is shown as the yellow shaded area. In this example, our test statistic is 2.5. The area in the right tail beyond 2.5 is about 0.011, and on the left side, beyond minus 2.5, it's also about 0.011. Together, this gives a p-value of approximately 0.022, which is smaller than our significance level alpha of 5%. Therefore, we reject the null hypothesis.
And what if the test statistic were smaller, say 1.5?
Then the area beyond 1.5 on the right would be about 0.078, and beyond minus 1.5 on the left also 0.078. Together, the p-value would be about 0.156. Since this is larger than alpha, we would keep the null hypothesis.
So in the end, whether we use critical values or the p-value, it's really the same decision, right?
Exactly. Different tools, same logic, we're always asking how compatible our data are with the idea of no effect under H0.
That makes sense. But there are so many different statistical tests out there. It feels impossible to learn them all.
And you don't have to. What matters most is understanding the principle behind statistical testing. Once you've got that, the details of specific tests are much easier to learn, and the software takes care of most of the calculations anyway.
So the real skill is to understand the idea, not to memorize endless formulas.